All right, in this section, we're going to go through and we're going to decide in each of the figures which graph is your original function, your first derivative, and your second derivative. And I'll just kind of talk through the process. Again, I'll label my original function will be in red, my first derivative will be in blue, and then my second derivative will be in green. Okay. So in figure one, I first and foremost, I kind of have a feeling about this because we know from derivatives in general that these all look like polynomial functions of some sort. I have a cubic function, a parabola, and then a linear function. And so my first jump to is that my cubic function will be my original, then my parabola will be my first derivative, and my linear will be my second derivative, because typically you would go down the line, you'd go from a cubic to a parabola to a linear function. But let's just talk through the shapes of the graphs and kind of talk about what that means. So on my original function, or what I think is my original function, I can examine a couple of different things about it. First of all, my original function is increasing, 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 increasing. So if I'm looking for the derivative of this graph, which I'm mad that I didn't draw that neater, if I'm looking for the derivative of this graph, I need to find something that is only positive, because my entire function is increasing, and so my first derivative would be positive. And so when I'm looking at my linear function and my parabola, this is all in the positive section, so that would work for my first derivative. It also makes sense because of how my original function is increasing. So it starts off pretty positive, then it's a little less positive, less positive, less positive, almost zero. It almost looks like it has a saddle point here. And then it goes to more positive, more positive, more positive. So pretty positive, pretty positive, pretty positive, almost zero, and then more positive again. So that makes sense. And then let's just examine our second derivative. So you can talk about this in terms of either your first or your original. So I have a concave down graph until just about this point, and then it turns into concave up. So my second derivative graph would have to be in the negative section, because it's concave down, until this point where it has an inflection point, and then it would be in the positive section because it's concave up. So in the negative section, 0 at the inflection point, and then concave up. Beautiful. The green function, excuse me, is also I know that this is my second derivative because it's a very good derivative of my blue function, right? So my blue function was decreasing, 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 0. Hit a critical point, so had a slope of their tangent line would be 0, and then it starts increasing again, which means its derivative, the blue's derivative graph, would have to be negative until it hits 0 at that critical point, and then goes positive again. So this is my original function, this is my first derivative, and then this one is my second derivative. If you would like to pause and try the next couple of them, please do so now. Otherwise, I'm just going to keep working through them. Okay. So in this one, I can't tell as much because I'm just not as familiar with these graphs about which ones are which, right? I think this is maybe some kind of logarithmic function. This could be an exponential function, so I'm not sure. So I can't really base it off of that. So I'm just going to go ahead and I'm going to start looking at my concavity and my slopes and try to order it all out. So for example, this entire solid line graph right here, this is concave down, which means that my entire derivative of this would have to be, or excuse me, second derivative of this would have to be all in the negative section. So if I make this my original function, then that means that between my dotted line and my other solid line, my dotted line would have to be my second derivative. And so we're just testing it here. We're just picking one. Now I just have to see if this makes sense for this to be my first derivative. So if my original function is only increasing, only increasing, only increasing, only increasing, only increasing, only increasing, that's awesome, because then my first derivative would have to be only in the positive section. Not only that, but it's increasing. It starts off like with a really positive slope, and then it's still positive, but it becomes more and more slanted. So it had like a very steep positive slope, maybe like 6 or something like that, and then it goes down to 4, and then it goes down to 2, and then 1, and I'm just making up those numbers, but just to kind of see the numbers as they grow. And then, so its first derivative would have to be something that's all in the positive section of the graph, and that would be true here. Right? This is all in the positive section. It starts higher, so it starts at a more positive place, which means that it had a more positive slope, your original function did. And then your first derivative graph it still stays positive, but it gets less positive. Same way the slopes of your original function were still positive, but they were just getting smaller and smaller and smaller. So then if I make that my first derivative, then I just have to double check one more thing. If my if my first derivative is decreasing, that means that my second derivative would have to be all in the negative section. So I think that's true here, right? This is decreasing, which means my second derivative is in the negative section. So everything makes sense. I have my original function, my first derivative, and my second derivative. All right, in this next one, I'm looking and kind of, again, my gut instinct is that this almost like it's almost a cubic graph because it's got 2 bumps. This would be my original function, so that's what I'm going to go with first. I'm just testing it. So if I make that my original function is increasing only. So it's increasing. It looks like it goes from really positive slopes to like less positive slopes, and then it goes really positive again. So if that's my original function, the only option for my first derivative would be this guy, because this is the only one that's in my my positive section. Okay, so if I make that true, so if I make this my original function, this my first derivative, then I'm going to have to check and see if does this make sense as my second derivative. And so if I do this piece as my second derivative, well, let's see. My original function is concave down, concave down, concave down, concave down, concave up, concave up, concave up. So that means my second derivative would have to go from negative to positive, which it doesn't do. Okay, so I messed something up somewhere, and so this can't be my original function, and this can't be my first derivative. So let's pick another one to do. So let's see if this is my, which one do I pick? This one? Let's make that one my original function. So I have an original function. It's concave up the whole way, which means that my second derivative would have to be positive the whole way, so that means that this would have to make this my second derivative. And then also my original function is decreasing until it hits 0, and then increasing as far as its slopes go, right? I have a bunch of negative slopes, and then I have a slope of a tangent line, and then I have a bunch of positive slopes, which means that if I'm correct, my first derivative graph should be in the negative section, which it is, then it should hit 0 here, which it does, and then it should go into the positive section. So that looks okay so far. The last thing I do want to check though is that it makes sense for this to be my second derivative. So if from my first, so if I have my first derivative, it's positive. Oh, excuse me. I take that back. It's increasing, which means that my second derivative would have to all be in the positive section, which it does. So it does make sense that this is my first derivative graph. Oops, that's close enough. This is my second derivative graph. And then this is my original function. You just get better at it as you go, right? So you're just kind of identifying the important pieces. All right, in this one, g prime is not shown, so you're only going to be relying on your original function and your second derivative. So I'm going to be looking at a lot of concavity things and comparing those two. So for example, if I look at this guy, well, let's look at this one. So this one is concave up until concave up until here-ish, and then it's concave down. So that would have to mean that my second derivative graph was in the positive section, then went to the negative section, which this dotted line does not do. So let's look at it the other way. This is a concave down graph, concave down until about right here, maybe here, and then it goes concave up again. So that means that if this is my original function, why do I use F? Oh, was I supposed to use F? No, that was very good. G delta prime. So if this is my original function, concave down and then point of inflection and concave up, my second derivative graph would have to be in the negative section and then 0 and then positive section. Negative section, 0, positive section. And it is. So that makes sense. Close enough.